Hi students, I'm Satish Kumar. In this lecture, I'm going to tell you the potential difference due to a point charge. In the last lectures, we have seen work done due to a point charge in an electric field or work done in moving a test charge against the electric field by an external source. And then we have seen the properties, and from the work done, we have got the expression for the potential difference. Now we need to find out the expression for the potential difference, which we have denoted it as VAB due to a point charge which is responsible for the electric field that I denoted by Q. So this is that point charge which is responsible for this particular field, which I am showing, which I have shown with this circle, which is actually a spherical surface. So now we have to assume a spherical coordinate system because the shape of the electric field is obtained as a sphere. Now, this is the point A where I have to finally brought the test charge, and this is the point B, which is the initial position of the test charge, and this we call it as the final position, and this is the place where the test charge has to be moved. Now what we have to do is we have to start with the expression of potential difference that we got. In the last lecture, we have seen that the potential difference expression is, which is denoted by VAB, which is equal to, when we made the test charge is equal to 1 coulomb, and VAB will be equal to simply minus integral B to A E dot dl. E dot dl. This is the expression that we have got for the potential difference. Let us call this is equation number 1. Now our intention is to get this VAB in terms of these distances. If you observe, the distance from the center of the sphere to the point A is denoted by RA, and from the same center to the point B is denoted by RB. Okay, and the charge here is Q. We have to get this VAB in terms of this RA, RB, and the charge Q. How do we get that? Here, our title itself is potential difference due to a point charge. So, E may be varying or may be different at RA and RB, but the radial distance here is R. So, E due to a point charge, which we know is, first let us try to write that, E due to a point charge. E due to a point charge is E equal to, which we have already calculated, which is Q by 4 pi epsilon. Let us take it as small r, which is the radius of the sphere, AR vector. Now, this is our expression for the electric field intensity, which is in spherical coordinate system, because here AR is the unit vector in the radial direction. For the spherical coordinate system, the coordinate is r, theta, and phi. The unit vector along radial direction is AR, and in the theta direction is A theta, which is an elevation angle, and azimuthal angle is A phi vector. Okay, so this is AR is a radial direction unit vector. Now the DL vector in the spherical coordinate system is, we know very well that we should remember this dl vector by using the incremental lengths in the direction of r, theta, and phi. So the incremental length in r direction is dr. Let us try to write that. And theta direction is rd theta, and in phi direction is r sine theta d phi. So for writing dl vector, what we require is simply dr AR vector plus r d theta A theta vector plus r sine theta d phi A phi vector. Okay, so this is a very big one, but you have to remember. So now you have to find out E vector dot dl vector and substitute in this and try to put the values of B and A. Then we have to find out VAB, right? So what we get here is VAB will be equal to minus integral. Let us keep this B to A as it is. And E will be Q by 4 pi epsilon R square A R vector. Put this in a bracket. Dot product with R dr AR bar, dr AR vector or bar plus R d theta A theta bar plus R sin theta d theta A phi bar, right? So let us close this, right? Now, if you observe, we know the dot product will be always when AR dot product with AR is only 1, and the dot product of different unit vectors will always be 0. That is, AR dot product with A theta is 0, and AR dot product with A phi is also 0. Now what you will be getting is this minus q by 4 pi epsilon is just a constant. Bring this out of integration. Now integral, let us try to write what is this B and A. But what is left here? AR dot AR is only 1, remaining will become 0. This we don't require. Now what is left here is 1 by R square is left. AR dot AR is 1. Here what is left is dr. Okay. Now integral here is with respect to R. So the limit here is lower limit is B and upper limit is A. If you come back to your diagram, the distance from the center of the sphere to point A is RA, that is R is RA, and from center of the sphere to the point B is RB. So here R is RB, here R is RA. So we have to simply substitute that. B to A means R is equal to RB, A is R is equal to RA. What is integral of 1 by R square is? It is minus 1 by R. So what is left is Q by 4 pi epsilon into integral of 1 by R square dr will be absolutely minus 1 by R. So it is minus 1 by R. The limits are from RB to RA. If you bring this minus outside, that's minus into minus will become plus. So what is left is Q by 4 pi epsilon into 1 by RA minus 1 by RB. And this is the expression for the potential difference VAB, and call this is 2 equation, and the units will be volts. Now they can further expanded this as VAB is equal to Q by 4 pi epsilon RA minus Q by 4 pi epsilon RB. It is simply showing that this is the expression for potential at point A, and this is the expression for potential at point B. So we can further write this as VA minus VB. That's what I said in the beginning. This representation is purely in our hands. Whether you represent this as VAB or VBA is purely our wish. So what we finally got is VAB is equal to VA minus VB, which is a potential difference, and which is absolutely in terms of charge and RA and RB. Okay, so this is potential difference due to a point charge Q. Okay, that's the end of lecture, and we will try to see the problems all at a time in one lecture. That is on work done, potential difference due to a point charge, and absolute potential. All we'll see one by one at a time. Thank you. If you like my video lectures, once again I'm requesting, please subscribe my channel. Thank you very much once again.